This is section 9.4, graphs of the other circular functions. Okay, so we've already talked about how to graph sine and cosine, and those are very important graphs for our consideration. We do use those two the most, and they will also help us today in graphing other trig functions. So let me quickly do a sketch of those two, and these are two sketches that you ought to be able to do soon very well. These two sinusoids are that important. So I would mark off the x-axis every pi over 2, unless there's a period change, but right now we're assuming we have the basic vanilla graph, y equals sine of x and y equals cosine of x. Make your marks on the y-axis by 1. Set up both of them. Okay, so let's do y equals sine of x first. Sine of 0 is 0, which means we start at the middle value, and then at the next mark we'll go to the high, middle, low, middle, going the other way, low, middle, high, middle, and graph the sinusoid. Nice smooth curve. And then we'll graph y equals cosine x. Cosine of 0 is 1. So the cosine graph starts at the high of 1 and goes middle, low, middle, high. The other direction, middle, low, middle, high. And there's our sinusoid. Nice smooth curve. Okay, so to graph, I guess we can start with cosecant of x. What I'm going to remind you of is one of the identities we've already talked about. The reciprocal identity is that cosecant of x is the same thing as 1 over sine of x. And since the domain, I'm sorry, not the domain, the range of sine of x, and cosine of x, by the way, is -1 to 1, that means that all of our reciprocals of those numbers that are between -1 and 1 will give us answers down here. The range will be from the reciprocals of the numbers between 0 and -1 are -infinity to the reciprocal of -1 itself is -1, union, and then the reciprocals from 0 to infinity are, excuse me, I misspoke. The reciprocals of the numbers from 0 to 1 are, the reciprocal of 1 is 1 itself, and the reciprocal of the smallest number is getting really big, so it's headed towards infinity. So that's the range that we were able to find before. We argued about argue in this mathematical argument in the sense that we talked about this range, but I said it won't be until we graph it that it really starts to make a lot of sense. So I think this is where the range that we've seen before will make more sense than it did when I just stated, oh, this is what it is, pretty much. So let's plot some points. For one thing, it's not a bad idea on this to have the sine graph represented. So I'm going to repeat that really quickly. I'm going to try to make it a much smaller and not as significant of a curve because it's not the answer. So sometimes my pen cooperates and sometimes it doesn't. So anyway, that's sine of x again. the reciprocal, well, this is where I'd like to start. The reciprocal of 1 at pi over 2 is 1. And every place where y is 1, its reciprocal will be 1. So over here, it'll be 1. Then over at 3 pi over 2, where the sign value is -1, the reciprocal of -1 is -1 itself. Those are the places where the ranges meet. Then, halfway between those is a y value of 0. And of course, sine of x being 0 there indicates that we'll be calculating the cosecant value by trying to take 1 over the value 0, which is undefined. And where that's undefined, I would like for you to put a vertical dotted line, because that's the place where the cosecant graph is undefined. So every time sine of x is 0, we're going to put a vertical asymptote. Okay, and of course there'd be infinitely many of these. And what that implies then is that the same places where sine of x has its x-intercepts, that will be the location of the vertical asymptotes for cosecant. So we'll have vertical asymptotes at x equals multiples of pi. Okay. All right. So then consider that between 0 and pi over 2, we know that the sine of pi over 6 is 1/2. And I'm picking on that one because it's a nice rational number, does not involve a radical, and its reciprocal is a nice number. So at pi over 6, the reciprocal of 1/2 will be graphed as a 2. And at 5 pi over 6, the same thing happens. Sine of 5 pi over 6 is 1/2, so the reciprocal of that is 2. And these are fractions of pi that I'd like for you to memorize. It is for here fractions of pi, but if we have a period change, that will alter. But the fraction is what I want you to pay attention to on this. From left asymptote to right asymptote, 1/6 of the way, you'll either have 2, and you'll see in a second -2 is the other possibility, and 5/6 of the way, you'll have the same value again. So think about from the y-axis to the first asymptote to the right, that's from 0 to pi. At pi over 6, 1/6 of pi, you have a value of 2, and 5 pi over 6, 5/6 of the way from 0 to pi, you have the value of 2. And those fractions, 1/6 and 5/6, are things you need to kind of put into your head. And the closer the sine value gets to 0, the further the answer will get from 0 when you take its reciprocal, and you'll get something that looks kind of like this. Now let me caution you, that is not a parabola, because a parabola is not limited on either side by a vertical asymptote. And the curvature is actually different. It reminds you very much of a parabola, it's just not a parabola, so be careful about jumping to a bad conclusion. So 2 pi before that, the exact same thing is going to happen. Between left and right hand asymptote, 1/6 of the way, the answer will be 2, and 5/6 of the way, the answer will be 2. And of course, what I'm using is that our period is 2 pi, so I went back 2 pi and got the exact same answers. So I'll go ahead and say that too. The period is 2 pi. Now, for the other two intervals where we have a -1 in the middle, go over to the far right. That one, 1/6 the way, the sign value is -1/2, so the reciprocal is -2. 5/6 the way, same thing, -2. And so this will be kind of a downward pointing branch of this curve. And 2 pi before that, the same thing will happen. 1/6 of the way will be -2, 5/6 of the way, -2. And there you go. Okay, so One other fraction that I'd like for you to pay attention to is that halfway from one asymptote to the other, you'll have either 1 or -1. And that'll be a place where the sine curve is at its maximum, at its high point. That will be the low point of the cosecant curve. Or, if you're between the other pair of asymptotes, sine of x is at its low point of -1, which is the high point of the curve opening downward that's at -1. And so those 2 points always agree for the two curves. Well, that's what that one looks like. Let me see if there's anything else that I'd like to say about that. I'll come back to that probably in a few minutes. What I'd like to do now is let's look at the secant curve, and we're going to find a lot of similarities. In fact, all of the cofunctions have very similar graphs. Sine and cosine have a very similar graph. They're both sinusoids. The reciprocals of those sinusoids always give you the same look. This up branch, down branch, which makes one cycle. And then it repeats up branch, down branch, up branch, down branch, etc. Okay. Oops. Okay. So again, I'm going to draw in the cosine curve, and this is actually a pretty good idea when you're trying to draw secant or cosecant. Start by drawing its reciprocal function, cosine or sine, whichever one you happen to be working on at the time. Since it's secant, this will be the reciprocal cosine. And then use that to help you find everything about it. Now, as we said before, the place where cosine is equal to 0, the secant graph, because it's the reciprocal of cosine, will have you dividing 1 by 0 when cosine of x is equal to 0. So at every place where that happens, where we're at a middle value, we're at the x-intercept, where the value is 0, we'll have an undefined secant value. And we'll draw vertical lines to represent that we cannot use those values of x, because that makes for the secant graph a division of 1 by 0, which does not give a real number. Okay. Okay, every time cosine of x is equal to 1, its reciprocal will also be 1. This should all sound familiar. And every time the cosine graph is -1, the reciprocal of -1 is -1. Okay. And let's do the one in the very middle. From left asymptote to right asymptote, 1/6 of the way, the answer will be 2. And 5/6 of the way, the answer will be 2. And plot that upward pointing branch. Moving to the right, 1/6 of the way from pi over 2 to 3 pi over 2, the answer will be -2. And 5/6 of the way between those asymptotes, it will be -2 again. And draw the downward pointing branch. So because of the way this worked out and the marks I put on here, on the right end of this, we're only getting half of the entire branch because I stopped it at 2 pi. So we'll have to kind of imagine what that 1/6 of the way, since I don't have the right-hand asymptote drawn, that should be 2, and that will be an upward pointing branch. If you can't stand it, you can put another mark and another asymptote and have another half of that upward pointing one, but I don't think it's necessary. I think you're okay. Back over here, between these asymptotes, 1/6 of the way and 5/6 of the way, we'll get -2. And the far left, we'll get half of a upward pointing branch again, like that. Okay, so where are its vertical asymptotes? They're at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative 1 pi over 2, negative 3 pi over 2, negative 5 pi over 2. Remember what those are? Those are odd multiples. Remember how to write odd number? 2n is even, plus 1 makes it odd. Odd multiples of pi over 2. That's where the vertical asymptotes are. And of course the period of this one is 2 pi. So from negative 2 pi to 2 pi, which is what I graphed in both cases, I got 2 full cycles. Half of an up, down, and half of an up make a full cycle, and then repeating that gives you a second cycle. All right, so let's see if there's anything that I left out. Nope, that looks good. Let's see. Oh, one thing that's true about both is there are no x-intercepts. Because, of course, look at the range. We skip from -1 to +1 in the statement of the range over here. So we get no values for secant or cosecant that are between -1 and 1, which, of course, 0, which is between -1 and 1, is never used. So I probably should have color-coded that with red, but oh well, don't worry about it. Now, there is no amplitude for these graphs because although we do have a middle at 0, which is not even a value on the curve, but it's in the middle of it, if you will. The distance from the middle to the high is impossible to measure because the high value doesn't exist. So we can't calculate an amplitude. If you want to use their definition, half of the distance between the two, you'd have to have a maximum and a minimum, neither of which we have. So amplitude is not something we talk about in terms of secant or cosecant. In fact, that's only used with sine and cosine. Let's talk about symmetry for cosecant. If there's a point anywhere on the curve that I want to pick, there's either, if there's going to be symmetry, one of the two symmetries, there's either going to be a point right on the other side of the y-axis from it, which for the cosecant curve doesn't happen, or a point across the origin from it, everywhere. And that's actually true. So this is an odd function. So the implication is if it's odd, it's symmetric with respect to the origin, and f of -x equals negative f of x. So that means that the even-odd identity for cosecant is, because it's odd, the cosecant of the opposite of x gives you back opposite of cosecant of x. So you need to go to that other place where we wrote the odd-even identities and write this one in to the right of the one for sine of x. Okay, and then for the other graph, the secant graph, pick any point you want, and is there a point on the other side of the y-axis from it to match it? Yes. That means it's an even function, symmetric with respect to the y-axis, and so that means that f of -x equals f of x. Specifically for this being secant, this is secant of, the implication is secant of -x is equal to secant of x. And so as it turns out, since sine is an odd function, its reciprocal is also an odd function. Cosine is an even function, and its reciprocal function is also even. And so that's one way to help remember these, is that the reciprocals of our sine and cosine have the same behavior as far as symmetry is concerned as its reciprocal does. Okay. see. All right. Now, now that we know what the basic graphs for cosecant and secant look like, let's talk about how to graph if we have some transformations going on of those curves. So what I'm going to suggest we do, and you can see this suggestion is right after the cosecant functions particulars are listed. There's a page where it says guidelines for sketching graphs of the secant and cosecant functions. So they're talking here about the multipliers a and b, which will stretch or shrink vertically or reflect vertically by a's value, and b will have it stretch or shrink horizontally, the opposite way of what you would think. Or if b were negative, which won't happen in this book, it would reflect over the y-axis horizontally. So what we're going to do as a guideline is we're going to graph a guiding function using the reciprocal. So if we want to graph y equals a cosecant of bx, we'll first graph y equals a sine of bx, and then use that to guide us to get the graph. So let me show you how that works with an example, because I think that's going to be probably the easiest way for those guidelines to make sense. So read through those guidelines as I'm talking about this graph, and then maybe look at it again and go through the steps of graphing and make sure that you understand everything I did. Okay, so let's say that we wanted to graph y equals 2 secant of 1/2 x. So the guiding graph will be y equals 2, what's the reciprocal of secant? Cosine of 1/2 x. So we're going to graph that to guide our endeavors in getting the graph of the secant. All right, so if we're going to graph the cosine curve, we would start with a, and we would say the amplitude of the cosine curve is the absolute value of a, so the amplitude is 2. The period will be the base period of the function 2 pi over the coefficient of x, which is 1/2. So that means the period is 4 pi. And then we're going to divide the period by 4. Now I'm not going to do the other two things in this particular example, because really this is supposed to be getting us towards graphing y equals a secant of bx. The c and d are not part of this particular example yet, so I'm just not even going to write those things, but those would be considerations that you would make, of course. All right, so I'm going to make this graph a little bit more spread out so that it's easier to see what's going on, so I'm using a much wider scale. My pi over 2 I'm going to make fairly big. And again, that's in an attempt to make it easier to see what's going on. All right, so I would start by graphing the guiding function. Cosine of 0 is 1. It's the high value, but that's then multiplied by 2. So we're at the high value of 2. Of course, the amplitude is 2, so that makes sense. So after that, you'll get the middle, the low, which is 2 below the baseline, middle, high, 2 above. Going this way, middle, low, middle, high. And again, making sure I do the amplitude of 2 every time. Oops, kind of missed that point. Graph is kind of slipping a little bit from my control. Oh, no, it's okay. It's not perfect, but I think it'll do. Okay, so after you have the guiding one drawn, then, oh my goodness, I just did something really bad. I didn't pay attention to my own instructions, but all is not lost. And this is one cool thing about doing the graphing the way I'm doing it. That pi over 2 I wrote, I did that sort of as an automatic response, not even thinking about what I was doing, and I messed up. So I did the calculation for the period divided by 4, and then I forgot to use it. So let's go back and make that right. That mark should be at pi instead of pi over 2. So luckily, I was able to recover from that mistake pretty easily, and because the thing I'd messed up was not the amplitude, but the period, and changing the frequency of those marks on the x-axis fixed it. So yay for me, got it right. Fine. Well, didn't at first, of course. Then the next thing I would do is every place where you're at the middle value for the guiding function, at that 0 right there, draw a vertical asymptote. And if you're asked to identify a formula for those asymptotes, you should be able to do that. I'll show you how in a second. Of course, my graph right there wasn't that great, so please pardon the negative pi. Should be an x-intercept, which I sort of messed up. So what are all these asymptotes? Pi, 3 pi, 5 pi, negative 3 pi, negative 5 pi. If you're asked, and you might be, the vertical asymptotes are at x equals odd multiples of pi. Odd multiples of pi. Okay. So, let's see. After you've done the asymptotes, to graph the function, let's start right at the y-axis. That y value is 2 when x is 0. The reciprocal will not be made of 2, which we're actually going to think of the regular secant value, which would be 1 there, and then multiply it by 2. That's what this says right here, is 2 times the secant of the ordinary one. Well, the easy way to do that is just whatever that high point is, that's the low point of the upward pointing branch. So every one of these dots at the highs and lows of cosine are going to be points on the secant graph. Okay. Now, 1/6 of the way we would have expected a value of 2. When we double that, we'll get 4. So that's that stretching. And 5/6 of the way, we'll get double 2 is 4. So that's the stretching factor of that 2 in front of the secant curve. It takes all of the normal outputs, 1 and 2, and doubles them to be double 2 is 4, double 1 is 2. Okay, same thing for the downward pointing. Double negative 1 is negative 2, which is where that low, that high point on the downward pointing branch will be. 1/6 of the way, we expect it to be negative 2. Double that, you'll get negative 4. 5/6 of the way, negative 4. And of course, once you get that going, repeating it for another cycle is no big deal. The thing that you might not like as much is that we are going to have only a half cycle over here to the right, unless you drew another mark and expanded it. And same thing over here. The same thing is going to happen. You'll have half of one over here on the far left. And then this downward one, halfway will be, 1/6 of the way is negative 4, 5/6 of the way is negative 4. Halfway is the doubling of negative 1, which is the negative 2 that's graphed there in the middle, that high point of this curve I just drew. All right, so there is the graph of that function. All right. So let's do another one. Again, I think the understanding of this comes more through seeing this graphed than anything else. So I think that's what really going to help. Oh, one thing I forgot to do was to kind of color code. I meant to write this in green and I forgot. So I'll put a green dot there saying the graph of that function is in green. And down here I'll do it correctly. Since I'm thinking about it right now, I'll do it. Okay, so the one we're supposed to graph is y equals 3/2 cosecant of x minus pi over 2. Okay, so the guiding function is y equals 3/2 times, what's the reciprocal of cosecant? Sine of x minus pi over 2. So we just take out the cosecant, put sine in its place, or take out the secant and put cosine in its place to graph the guiding function. Okay, so the amplitude of this one is 3/2. The period, since there's not a number in front of x, is going to be 2 pi divided by an understood 1. And so that means that the fourth of the period, the markings, horizontal markings between major events, is going to be every pi over 2. Okay? And of course, we need to remember that because of that x minus pi over 2, that we're going to shift, have a phase shift. I'm going to put PS here for phase shift. The phase shift is equal to pi over 2 to the which way? To the right. And if you're in my math lab, you'll write positive pi over 2. If it had been x plus pi over 6, plus pi over 6, then it would have been pi over 6 to the left, and in my math lab you would have written negative pi over 6. Kind of reminding you of that because it is an oddity that they do that way. And I always like to point that out over and over again so that it sinks in. Okay, this time I'm going to think about this better. Each mark on the x-axis needs to be what? Look at the period over 4 statement, and that should answer your question. It's pi over 2. Okay, pi over 2. All right, so to graph sine, the sine of the 0 value would be a 0, which would be a middle value. And 0 times 3/2 is still 0. And then that point that still is at 0, 0 is going to be shifted pi over 2 to the right. So move it to right there. Now, after the value where x is 0, we would expect, if we go to the right, to go up 1. That's true as long as that 3/2 is positive, and it is. So we'll go up 1, but wait, 1 is supposed to be multiplied by 3/2, so make that 3/2, 1.5, as the high. If that had been negative 3/2, we would have gone to a low instead of the high to start with. So next mark over, back to middle. Next mark, low, which is, don't forget that low is 3.5 below. Okay, so going to the left, this will be low. Oh, darn it. I just said make sure it's 3/2 below, and then I messed up. Low, middle, high, middle, low. Then draw the curve, sinusoid that goes through those points. Wow, I've seen better curves. I've done better curves. Well, the good news is I can be pretty forgiving on these. As long as I can tell the attempt was made to make it correct, I'm going to be all right. Just try to make it look like a nice smooth curve. Unlike mine, this pen doesn't work as well as a pencil does for me. So anyway, look for the middle values. The reciprocal of that 0 middle value will give you the vertical asymptote. And you may be thinking about what is the equation of these vertical asymptotes in case someone asks me. Did you get them yet? Yeah, the vertical asymptotes are at odd multiples of pi over 2. Okay, so every time the sine curve is at its highest, the cosecant curve will be at its lowest. So we'll get those same dots at the high points of the sine curve. Will be a dot on the upward pointing branch. 1/6 the way, we'd expect a value of 2, but we're multiplying by 3/2. 2 times 3/2 is 3. So 1/6 of the way and 5/6 of the way, we'll get 3. Same thing over here, 1/6 of the way, we'll get 3. And again, that's because it's 3/2 times the expected 2. 3/2 times 2 is 3. And then you can draw the nice smooth curves that open upward. Like that. Then for the downward pointing ones, every low point of the sine curve is a high point on the cosecant curve. Let's do the one in the middle. The expected outcome 1/6 of the way is -2. 3/2 times -2 is -3. And so 1/6 of the way and 5/6 of the way will be at -3 for the downward pointing part. And so that'll happen over here as well. 1/6 of the way will be at -3. And 5/6 of the way will be at -3. And so those two half downward pointing ones make one whole one. So we've got up, down, a period, up, and then half a down and half a down is a full down. So we actually have 2 periods graphed. And that's usually the minimum I want to see. If you wanted to graph more, I would not be upset. But this is like the absolute least I will ever want you to do, unless the directions say just graph one cycle or something like that. That's all you'd have to do. Okay, so let's now go to the other two trig functions, tangent and cotangent. Okay, so you're going to have to think about the sine and cosine graphs as we do tangent, because what I'm going to use is the ratio identity, or the quotient identity for tangent is sine of x over cosine of x. And of course, the danger in having a fraction is that the denominator can't be 0. So cosine of x can't be 0. And if you look back up at where cosine is 0, let's go back and look that up. Go all the way back up here to the beginning. Look at the cosine curve. It's 0 at odd multiples of pi over 2. So for the tangent graph, because we can't divide by 0, x can't be an odd multiple of pi over 2. Okay? So the tangent curve, consequently, since those are undefined values of x for the tangent curve, those odd multiples of pi over 2, those will be locations of our vertical asymptotes. So draw in at pi over 2 and every other odd multiple of pi over 2, a vertical asymptote. Okay, so let's see. Halfway between those asymptotes, and you notice that in these graphs, halfway between them, there's usually something going on that's of interest. So I did pick that on purpose. I want to do this with a table of values. So let me write that down. And once you know these values, you won't have to do this table. But 0 is a good middle between the asymptotes, when the very middle of all of our pairs of asymptotes centers at 0. And what is the tangent of 0? Right, it's 0. So that should be 0. And what we're going to infer from that is halfway between the asymptotes is always 0. So there are actually x-intercepts for this graph. And what are they? well, it's 0 and pi and 2 pi and 3 pi and negative pi and negative 2 pi. Yeah, that's multiples of pi. That's where the x-intercepts are for the tangent graph. Okay, now I'm looking for a value that's easy to graph. And when we have pi over 4, for example, the tangent of pi over 4 is 1, which is really easy to graph. So at pi over 4, whoops, I didn't put a y scale on this, pardon me. At pi over 4, we should graph 1. And at negative pi over 4, the tangent of negative pi over 4 is negative 1. So at negative pi over 4, graph negative 1. And the closer that x gets to an odd multiple of pi over 2, depending on which side of the asymptote you're on, the graph is either going to be headed towards negative infinity or positive infinity. And the 3 points I have graphed here are actually very good for that. We're going to go from negative infinity towards that negative 1, go through 0, 0, and then go up through that point at pi over 4, 1, and go up towards infinity. So there's what that graph looks like. So important fractions here to pay attention to are 1/4 of the way, it's negative 1. Halfway, it's 0. And 3/4 of the way between the asymptotes is a positive 1. So the cosecant secant fractions are 1/6, halfway, and 5/6. For tangent and cotangent, it's 1/4, 1/2, and 3/4 are the important fractions of the way between asymptotes. So that tells us that from pi over 2 to the next asymptote, 1/4 of the way between them, I'll put a negative 1, and 3/4 of the way, I'll put a positive 1. One way to remember this is if you can keep in your mind that tangent of x is an increasing function on its domain. Tangent of x increases on its domain. That means that the graph, as you move from left to right, it's going to be going upward as you go from left to right. And every asymptote, you get a restart. It goes from negative infinity to positive infinity, which of course means that the range is all real numbers, because we're going from negative infinity to positive infinity. Okay, let's see. What's the period? We may have noticed I've already graphed 2 of these. And how far is it from, say, pi over 2 to 3 pi over 2? Because that completes one cycle. Well, the distance there is 3 pi over 2 minus pi over 2 is 2 pi over 2, which reduces to pi. So unlike sine and cosine and secant and cosecant, tangent and cotangent are different because their period is pi, not 2 pi. Okay, so if we wanted to graph more of these, we have 2, so you've actually done the minimum. You would just graph, I'm going to do one more, 1/4 of the way, negative 1, halfway 0, 3/4 of the way 1, and draw the increasing curve. That's all there is to graphing tangent. And in reality, I think the hardest part is getting the asymptotes in exactly the right spot. But once they're there, it's not that hard to get the rest of the graph done. Okay, so let's talk about symmetry. Pick any point on the curve. I don't know, how about this one right here? Is there a point on the other side of the y-axis as a mirror image of it? Is there a point right there on the curve? No, so it's not symmetric with respect to the y-axis. Is there a point across the origin from it? So go that distance and then go that distance exactly again. that point is a point on the curve. So that symmetry with respect to the origin, says that tangent is an odd function, and its even odd identity is therefore the tangent of negative x is negative tangent of x. Oops, forgot to write the equal sign. Is equal to negative tangent of x. So it's an odd function. Okay. I think that's it. And make sure you add that to the even odd identities. You should have sine and below that cosine, and then put this tangent below that. And we'll put cotangent to its right in a little bit. And I'll write all of those again presently as I'm summarizing those. Okay, well, let's do cotangent. So, for cotangent, think of the ratio identity, the quotient identity. That's cosine of x over sine of x. Since you can't divide by 0, we can't allow sine of x to be 0. And where does that happen? We'll look back up at the original sine curve we did at the beginning of this. It's at multiples of pi, 0, pi, 2 pi, negative 2 pi. So that means that for the cotangent graph, x cannot be a multiple of pi. Okay, so let's start graphing this guy. Okay, so I think we're ready. So the first thing I would do would be to graph multiples of pi as numbers we can't use. That is, they're going to give us vertical asymptotes. You may have noticed I was a little bit smarter this time. I know that the period's going to be pi because it was for tangent. And remember, the tangent and cotangent, those cofunctions have very similar graphs, so I'll use that to my advantage here. All right, so again, what you might start with is values. Let's try pi over 4. The cotangent pi over 4 is 1, so I'll plot that point. What's the cotangent of pi over 2? That's 0, so plot that point. And then what's the cotangent of 3 pi over 4? That's negative 1. Plot that point. So it looks like, again, 1/4 of the way, halfway, and 3/4 of the way something's happening. And we're actually getting the same three answers. 1, 0, and negative 1 were the same answers we got for tangent, but we got them in a different order. Going from left asymptote to right asymptote, this graph, which looks a whole lot like the tangent graph, but instead of being an increasing function, cotangent is a decreasing function. So as you go from left to right for tangent and cotangent, you're either going to have 1 or negative 1, 0, and then the other number. So it'll either go 1, 0, negative 1 for cotangent, or negative 1, 0, 1 for tangent. So halfway between there'll be a 0. So 1/4 of the way there's a 1, so that it can decrease, then to 0. Then 3/4 of the way it'll be at negative 1. And then draw this shape. this tangent or cotangent shape. Looks like this. Okay. So, let's see. Where are its x-intercepts? At pi over 2, negative pi over 2. There would have been one at 3 pi over 2 and negative 3 pi over 2. That's at odd multiples of pi over 2. Let's see. The period is pi, as we said for tangent. It's the same period for cotangent. So of the 6 functions, 4 of them have a period of 2 pi. Sine and its reciprocal cosecant, and cosine and its reciprocal secant. The tangent-cotangent graphs have a period of pi, which is different. So kind of keep that in mind. I forgot to say this with tangent. I said it earlier when we were talking about cosecant and secant. So let me just say it here. There's no amplitude associated with either of these two because there's not a max or a minimum, to use their definition, to say how far it is from the middle to the highest point. So there's no amplitude, except for sine and cosine, there is no amplitude. Let's talk about symmetry. Is there, for a randomly chosen point, a point on the other side of the y-axis from it that's on the curve? Nope. Is there one across the origin from it that is a point on the curve? Yep. So this is an odd function, which means that the cotangent of negative x is negative cotangent of x. So put this in with your even-odd identities, and now I'm going to summarize those before I forget about it. So these are the even-odd identities. This is something you should have in your list of things to memorize. We just did them piecemeal, so that's why I wanted to summarize so that you can see them all together at one time. Sine is odd. Its reciprocal function is also odd. Cosine is an even function. And its reciprocal function, secant, is also an even function. Tangent of negative x is negative tangent of x, so it's also an odd function, and its reciprocal is an odd function. So oddly enough, there are more odd functions in the 6 than there are even. It is not split half and half. 2 of them are even, cosine and its reciprocal. The other 4 are all odd functions. So anyway, these are the even-odd identities that you should have in your list of things that you're memorizing. All right, so let's see how we graph with transformations. Again, right after the cotangent is kind of summarized for you. Kind of the summary I made is pretty much the same thing. There are guidelines for sketching graphs of the tangent and cotangent functions, specifically y equals a tangent of bx or y equals a cotangent of bx where b is positive. So one of the things I want you to focus on here is the equation for period is not the same as it has been. For the first 4 that we did, sine, cosine, secant, and cosecant, the period is 2 pi, and the equation for the period is the base period 2 pi over b. For tangent cotangent, the period will be 1 pi over b because its base period is pi divided by b. So that's one really important thing to notice. To find the vertical asymptotes, you'll do basically what I did up here, where you might see a change. It won't be plain sine of x, it'll be something else, but wherever the denominator is equal to 0, we're going to have vertical asymptotes. So to find the vertical asymptotes, set the denominator function equal to 0, or not equal to 0, and solve for what x can't be. And that will give you the equations of the vertical asymptotes. So here, the vertical asymptotes are at those very places where x is a multiple of pi. That's where every one of those asymptotes for cotangent would be. Okay, so you can read those guidelines. I'm going to try to do my best to follow them and get the right graph. I'm just going to maybe do it slightly differently, but it'll be the same basic technique. Okay, y equals tangent of 2x. So one of the things I'm going to do with that is I'm going to rewrite that as the sine over the cosine, sine of 2x over the cosine of 2x. Okay, and that means that the cosine of 2x, when it's equal to 0, or we could say it can't be 0, we can say it either way, that's going to give us the vertical asymptotes. So when is cosine equal to 0? Do you recall? If you need to, look up there. When does cosine equal 0? That was odd multiples of pi over 2, right? Odd multiples of pi over 2. So that means that 2x cannot be an odd multiple of pi over 2. Now, if you want to solve for x to find out where the asymptotes are, you'll have to divide both sides by 2. And that's going to mean that x can't be an odd multiple of, what's pi over 2 divided by 2? Pi over 4. So that implies that the vertical asymptotes for this graph will be at x equals all odd multiples of pi over 4. Okay. You'll probably be asked, if you can find it, what's the amplitude? Well, there is no amplitude. That's kind of a trick question. Only sine and cosine have amplitude. So if you're asked to find the amplitude, if there is one, you need to say there isn't one. The period is going to be not 2 pi, but for tangent cotangent, the base period is pi divided by b, and pi divided by the number 2. That's the b value here. There's your period. And if we divide that into 4 parts, pi over 2 divided by 4 gives you pi over 8. And that's going to be the frequency at which something interesting is happening, is every pi over 8. So let's start drawing this graph. All right, so let's get this set up. Make sure you label the axes. I've been trying to be very good about that myself. I generally will put 4 marks on either side. That's just kind of a go-to for me. Generally will get me what I'm supposed to have. Sometimes it's more than what I need, but that's okay. So the period over 4 is pi over 8. So I'll make every one of these marks on this axis pi over 8. Okay, so let's see. The vertical asymptotes are odd multiples of pi over 4. So since a mark is pi over 8, how many marks make pi over 4? It's 2 of them, right? 2 pi over 8 is the same as pi over 4. So at 2 pi over 8, which is 1 pi over 4, an odd multiple of pi over 4, I'm going to have a vertical asymptote. The next odd multiple of pi over 4 is 3 pi over 8. That's the same thing as 6. Oh, maybe I should have given myself more room if I want to go that way. Let me make some alterations here. I'll make that axis go out further. Because I want to make this so that it's pretty clear what you're supposed to do. So let's see. So we said 3 pi over 4, 6 pi over 8. 1, 2, 3, 4, 5. 6 pi over 8 is another asymptote. Okay. Negative 1 pi over 4, which is negative 2 pi over 8. And the next one would be at negative 3 pi over 4, which is negative 6 pi over 8. But because I have 3 asymptotes, between each pair of asymptotes we'll get 1 period. And if the minimum is 2 periods of it, I think I've done enough. The way I did this, I ended up having 2 full graphs instead of a full one and half of one on the right side and half of it on the left side. That's why going out to that 6th mark was actually not a bad idea, so that we get 2 full cycles without having a full and 2 halves of a cycle, which I think is probably good. Okay, so looking at this, notice that between the asymptotes there are 3 places, which means we split the asymptote to asymptote distance into fourths, which is good because since it's tangent, we know it's increasing. That means that we're going to go negative 1, 0, 1. So 1/4 of the way graph negative 1, halfway graph 0, 3/4 of the way graph 1. Draw the increasing function through those points. Again, 1/4 of the way will be negative 1, halfway will be 0, 3/4 of the way will be 1. Draw that curve. Okay. And then if they ask you, well, where are the x-intercepts? You can look at your graph and you should be able to figure that out. 0, and then 1, 2, 3, 4 pi over 8. That's pi over 2. And then it'll be pi later because the period is pi, which will be 0. No, I'm sorry, the period's pi over 2, not pi, because we calculated that right here. So pi over 2 later, that's 4/8 later, will be at, we were at 0, then we're at 1, 2, 3, 4, and then at 8 pi over 8, which is pi. So at 0, pi over 2, pi, 3 pi over 2, 2 pi. That's multiples of pi over 2. Multiples of pi over 2. N times pi over 2. All right, so there's that one. So let's graph another one. This time it's going to be cotangent that we're focusing on. We're going to graph y equals negative 2 minus, ooh, that means we have a vertical shift. Yay! Minus cotangent of x minus pi over 4. Oh, we also have a phase shift. Nice. So we're getting to do a couple of things here. There is no amplitude. We do want to pay attention to the fact that that's negative cotangent because that's going to have that reflecting thing. So let me write that down. That negative is going to make us reflect vertically. So kind of keep that in mind, that when we're done, it should be a reflection of what we would have expected for positive cotangent. Let's see, A, B is 1, so the period is our normal period for cotangent pi divided by 1, which is pi. Then dividing that by 4 means that every pi over 4, something interesting on our graph is going to happen. So I'm going to go over here and write every pi over 4, I'm going to have a mark. So that's pi over 4. Okay. Let's see. Make this 1. A little bit more. Okay. Okay, so the phase shift is pi over 4 to the right. And remember, in MyMathLab, you'd write positive pi over 4 for that. And the baseline, I think that's the first one of these we've done with secant, cosecant, tangent, or cotangent graph. This is the first one of these we've done, and that'll be at y equals -2. So you may have noticed that I made more marks in the negative y region because I was looking over and I saw that baseline was -2. So I wanted to allow for that, so I put more marks down there because I know I'm going to graph below it. Okay, this is where our pretend x-axis is at our baseline. So it's going to be as if it were the as if it were the x-axis at y equals -2. Okay. So let's see. For cotangent of plane x, I know that I would do cosine over sine. And I would not be able to allow sine of x to be 0. So x couldn't be multiples of pi. Okay, but for this graph, we're shifting all of that pi over 4 to the right. So, whoops, I forgot to put the not equal to. So that means that for this graph, x can't be n pi shifted pi over 4 to the right. Okay. Another way to do that, more algebraically than what I just did, would be instead of writing cotangent of plane x, we could have started with cotangent of x minus pi over 4, which would be equal to cosine of x minus pi over 4 divided by, oh, I'm sorry, yeah, that's right, sine of x minus pi over 4. We would have said sine of x minus pi over 4 can't be 0. We'll move over here, which would mean that x minus pi over 4 couldn't be, or when is sine equal to 0? Multiples of pi. And then to solve for x, you'd add pi over 4 to both sides and get that same thing. So there are a couple of ways you can come up with that answer. So a multiple of pi would be 0, right? When n is 0, 0 times pi is 0. Plus pi over 4 is where we have a vertical asymptote, because that's what x cannot be. And by the way, if you're asked what are the equations for our vertical asymptotes, that's going to be at x equals n pi plus pi over 4. Okay, so when n is 1, we have pi plus pi over 4, which is 5 pi over 4. 1, 2, 3, 4, 5 pi over 4. We have another asymptote. And I really want one more asymptote to get 2 full cycles. So let's go backwards. What's pi over 4 minus pi? In other words, if n were -1, it would be negative pi plus pi over 4. That's negative 3 pi over 4. So that 1, 2, negative 3 pi over 4. There's another asymptote. If we've done everything correctly, there should be 3 marks between asymptotes for the cotangent and tangent graphs. that splits it into 4 regions, the quadrants, if you will. So this is looking good to me. Now, because it's cotangent, we expect it to decrease, but the negative in front of cotangent is going to have us reflect vertically over y equals -2. It's where the axis would have been. So 1/4 of the way for cotangent, since it's a decreasing function, I would expect it to be 1 above the baseline. But multiplying by -1 is going to reflect that over the baseline, and it'll actually be starting at 1 below. Halfway it'll be 0, and normally it would have been 1, 0, -1. -1 times 1 is, I'm sorry, -1 times -1 is 1. So at the next mark, it's going to be 1 above the baseline. Looks like this. Okay. So halfway, 0. Now I'll look at the one I've already done. 1/4 of the way should be -1. 3/4 of the way is -1. And what kind of graph is that when you've reflected cotangent over a horizontal line? It looks like a tangent graph, doesn't it? Because it's increasing. So that's what happens with tangent and cotangent. If you have a negative coefficient, it looks like it's cofunction because of that reflection. So that is the correct answer for that one. Okay, now another thing that you're going to be asked to do is to, when you're given a graph, determine its equation. So it's kind of the backwards version of this. Given the equation, find all the information and plot the graph. We're going to be going the other way. So let me move over here so I, oops, went a little bit far. See how far I can go. Oops, that's about it. Okay. Let's go way up here so I have more room. So ignore all that stuff to the left you can see. For right now, I'll just kind of say, oops, that's from earlier. Forget it. So, yeah. So let's just draw a little line here saying don't look over there. Stay to this side. All right. There we go. Okay, so if you'll look at the graph that they've presented as the question, you'll be in a lot better shape than if you rely totally on my drawing of it, because theirs is going to be way more perfect than mine. All right, so they have, looks like asymptotes at pi/2. So that's at pi/2. And at -pi/2. Okay. So that's at -pi/2 where the other one is. Okay, now one thing that we have to do very carefully is read the directions. They want us to find the equation. We're not allowing for a phase shift. So this isn't something that's been shifted left or right. It's not been moved that way. So that's going to actually help us a lot. Let me graph it, and forgot to finish the graph. This mark here, it's at 2. Oops, I didn't draw the y scale. That's 1, 2. So -pi/4, it looks like it's 2. At 0, it's 0. And at pi/4, it's -2. And it's going down like that. So but the first determination I would make is, I've seen a graph like that before. What type was it? There's the sinusoid, that's sine or cosine. There's the up branch, down branch thing, that's the secant or cosecant. Or there's this curve that looks like this, that's tangent or cotangent. So one of the things that we're going to have to think about is, if there's no phase shift, is it going to be cosine over sine, basically, or is it going to be sine over cosine? And what I would pay attention to here is at 0, since we have a point at 0, 0, which one of those two, when I put 0 in, will give me 0? Well, if I put cosine of 0 over sine of 0, I'm going to get 1 over 0, which is not 0. It's undefined. Okay, let's see if the other one works. What's sine of 0 over cosine of 0? Well, that's 0 over 1, which is 0. Bingo! That's the one. It's sine over cosine. So what we're going to use is tangent. Okay? Now, there are a couple of things we need to think about. What's A, what's B? And if there's a baseline, we need to figure that out. Well, since we have the middle value at y equals 0, there's not going to be a new baseline. So with no phase shift, this is my letters. With no phase shift, C is going to be 0, and because the middle is at 0, that means that my D in my equation is 0. Okay, that's a couple of things that I figured out already. Now, the next thing would be, what's the period? What's the period? Well, this graph goes from negative pi over 2 to pi over 2, and that's a complete cycle from negative pi over 2 to pi over 2. Well, just how far is that? Pi over 2 minus negative pi over 2, that's pi. The period is pi. Is that the expected period for tangent? Yes. And so, since the period is pi and the formula for period is pi divided by b, that must mean that b is 1. Okay? So, then our last consideration is, when we're looking at regular tangent, 1/4 of the way, what's our expected value? At 1/4 of the way, what are we expecting for tangent? Well, since it's an increasing function, we expect a -1 value, 1/4 of the way. And what we're getting here is a positive 2, 1/4 of the way. This point up here is at y equals 2. So what would I have to do to -1 to turn it into positive 2? I'd have to multiply it by -2, which means that A must be -2. So it's having the reflecting feature, which makes sense because this looks like a cotangent, but we determined because of what was happening at 0 with no phase shift that this has to be tangent. Well, that means that there's a reflection going on here, so the fact that A is negative totally makes sense. And it's -2 because what do you multiply -1 by to get positive 2? -1 times what number is positive 2? You solve that and you'll get A equals -2. Okay, so I think we're ready to write our equation. Therefore, y is equal to -2 tangent of 1x, or just x, minus 0 plus 0. That's the c and the d. So that's the equation that produces that graph. Okay? All right, let's do another one. And again, look at their graph for total clarity as to what's supposed to be going on. Mine's just a quick sketch of it. Just not perfect, of course. Let's see. So what does each mark on the x-axis represent? Because they marked the second one and they marked the fourth one. They didn't mark the first one. What is that first one? It's pi over 8. Okay? Just so you know, that's at pi over 8. And the graph has, they didn't draw it, but there is a vertical asymptote here, and one at pi over 2. Which means, by the way, that because this is a tangent or cotangent look, our period is pi over 2. And I'll come back to that in a second. But we're going from 0 for a vertical asymptote to pi over 2, and it completes the cycle within that range, and so the period must be pi over 2 minus 0, which is pi over 2. Okay, and at pi over 4 we're at negative 1. Here we're at 0, and over here we're at negative 2. Okay, one other thing I forgot to say, I read it and then ignored, didn't say it. In the directions they say there's no phase shift. No phase shift. Which, in my use of the letters, that means that C is 0. Now, since this is a tangent or cotangent kind of thing, and there's no phase shift, you should probably look at what's happening at 0. This is either cosine x over sine of x, or it's sine of x over cosine x. And at x equals 0, it should be undefined. So which one of those two, when you divide by sine of 0 or cosine of 0, makes it undefined? Well, it's this one. Cosine of 0 over sine of 0 is 1 over 0 undefined. And so it's that function that we're working with. So we're going to use cosine over sine of x, which is cotangent of x. That's the function we're going to use. Okay. Now, with a period of pi over 2, I know the formula for period of cotangent is pi over b. And if I solve that for b, I should get b equals 2. Okay. Where is the middle? In other words, where is our fake x-axis? Well, for cotangent, the middle value is supposed to be at 0, supposed to be on the baseline. So wherever that middle value is, that's your baseline. And that's y equals negative 1. And that implies that d is negative 1. Okay, then how far above the baseline is our value? Well, it's 1 above at the baseline and 1 below for the other one, right? So that means that a, or the absolute value of a, has to be 1. And then to determine whether a is positive or negative, is cotangent supposed to be, since we're using cotangent, is it supposed to be decreasing or is it supposed to be increasing? If it were supposed to be increasing, it's been reflected, and we need a to be negative 1. If it's supposed to be decreasing, and it is, that means that a has to be positive 1, because it is not reflected. It is decreasing, and it's supposed to be decreasing. So I think we're ready to write the equation for this one. Therefore, y equals cotangent, oops, don't know what I was starting to write there, cotangent of b, which is 2x, which is 2, so cotangent of 2x, and then no phase shift. A is 1, so there's an understood 1 in front of cotangent. I forgot to say that. And then we're going to move it down 1, so minus 1. That's the equation of that particular graph. Okay, let's look at another one. Okay, so let's see. This mark is at pi. And it looks like we have asymptotes. Again, they didn't show that the y-axis is 1, but it is. 1 at 2 pi. One at 4 pi. And notice they've only given us one cycle, which is fine. We should be able to figure it out from one cycle. At pi, the answer is 1. And it opens upward. And since that's 1, we would anticipate that 1/6 the way it's actually 2 and 5/6 the way it's 2. And midway between the next pair of asymptotes, at 3 pi, the answer is -1. And 1/6 the way -2, 5/6 -2 is what I see there. Okay, so that's what's given. This is what type of graph? It's either secant or cosecant, right? Okay, so it's in the family of secant x or cosecant of x. Since there's no phase shift, which I again read and forgot to mention, what's happening at 0 is what's supposed to happen at 0 because we haven't shifted it right or left. So secant is 1 over cosine of x. Cosecant is 1 over sine of x. Which one of those is going to get an undefined value when x is 0? Well, cosine of 0 is 1. 1 over 1 is 1. That's not undefined. The sine of 0 is 0, and that is undefined. So that means this is a cosecant graph. Okay. The middle point at pi is 1, and that's expected. If it had been 2, that would mean we stretched it by a factor of 2. If the other side, notice the middle of this is, I probably should have said that first, the middle of this one is the x-axis. That's the middle. Because the lowest point in the 0 to 2 pi range is pi is 1, and -1, so halfway between -1 and 1 is 0. So that's where the middle is. And 1 is above that is the expected value, so we're not stretching it that way, so we're going to assume that this is, the absolute value of A is 1. Now, to find out whether we have a negative, we're going to figure out if it's been reflected. Look at the cosecant graph that we did earlier. It's here someplace. Oh, there it is, right? Well, let's look at the basic cosecant one. Between the y-axis and the first asymptote to the right, it's got the up pointing branch. If we know it's cosecant, and from 0 to the first asymptote it points downward, that means it was reflected. But this one is pointing upward like it's supposed to. So that means that that A is going to be +1. Okay, from 0 to 2 pi it's opening upward as expected. So we're not reflecting this, and it's +A. What's the period? Well, the period is what it takes to go through having both an up and a downward pointing branch. And that's from 0 to 1, 2, 3, 4 pi. So the period length is the right minus the left, 4 pi minus 0. The period is 4 pi. For cosecant, what's the base period? Well, it's 2 pi, right? So 2 pi divided by b. So I'm going to use that trick I taught you earlier, that if you want to solve for the denominator when a fraction equals a number, you can just switch the denominator with that number. I'm going to switch the 4 pi with the b and simplify. B is 1/2. This one has a middle at 0, and the fact that the middle is at 0 implies that there's no vertical shifting, so D is 0. All right, so I think we have everything we need to write the equation of this one. Therefore, y is equal to a, which is 1, cosecant of 1/2 x. There's no phase shift, so we're not adding or subtracting anything from that x. And d is 0, so plus 0, which doesn't change it. And this is the equation that we were looking for. All right. Now, last one. Determine equation, no phase shift. Okay, I'm going to write that down first this time. Which in my way of doing things means that C is 0. All right, so let's look and see what we have. They have a mark every pi over 2. Let me see. This is 1, 2, -1, -2. Okay, let's see. Let's graph what they have there. They have at negative pi over 2 vertical asymptote. At pi over 2 vertical asymptote. 3 pi over 2 vertical asymptote. And at 0, they have an answer of 2, and it opens upward. And at pi, they have a value of 0, opening downward. Okay, so the low point of the upward pointing one is 2. The high point of the downward pointing one is 0. What's halfway between 0 and 2? Well, that's 1. And so that means that this is where our fake x-axis is at y equals 1. And because that's going on, in my way of doing things, I call that d. That means in the equation, d will be 1 for me. Then, since the distance that is above is 1, which is what we expect, that means that the absolute value of a is 1. And also, we can check over here, this high point on the downward pointing one is 1 below the middle. So again, it's the expected 1. Let's see. I'll come back to that a in just a second. What I see happening at 0, since this is either a secant or cosecant with this upward downward pointing branch thing, if it's secant, then it's 1 over cosine. If it's cosecant, it's 1 over sine. And what's happening at 0 needs to be true. So what's 1 over cosine of 0? Well, that's 1 over 1, which is 1. 1 over sine of 0 is undefined. And so that's not what's happening at our y-axis. So it's a secant graph for sure. Because it's the answer of 1 I got, that means it's 1 above the baseline, by the way. It happens to be a value of 2, but it is 1 above the baseline. And so, and that's what we'd expect. If you look at this, at the secant graph, the one that straddles the y-axis, where did we do that? Right up here. The one that straddles the y-axis for secant of x points upward, which is what ours is doing. So if the one that straddled the x-axis or the y-axis were pointing down, we would think a is -1. But because it's pointing up as expected, that's going to imply that a is +1. So we've got c is 0, we've got d is 1, we've got a is 1. I got to find b. Let's see, what is the period for this one? We're going from negative pi over 2 to 1, 2, 3 pi over 2. How far is that? From negative pi over 2 to 3 pi over 2. Well, the distance is the right minus the left. 3 pi over 2 minus negative pi over 2 is 3 pi over 2 plus pi over 2, which is 4 pi over 2, which is 2 pi. And that is the normal period of the secant graph. So in other words, if we set the period we have equal to the base period for secant cosecant is 2 pi over b, and solve for b, we get that b is 1. Okay, so what's the equation then for this? Y equals a, which is 1, times secant, so secant of b, which is 1 times x, so x, minus c inside the parentheses with the x, well, c is 0, plus d, which is 1. And that's our equation. Y equals secant of x plus 1. Okay, that ends these notes. I will see you in class.